Okay, we're going to continue on here, and last time we got a little bit into talking about some types of reactions or ways to classify reactions. So we're off to here, chapter 7, and we're going to pick back up, I think, with the beginning of it, since we talked a little bit about the other one. But there really is, as I talked about, really two big sort of classifications of reactions. As we talked about at the end there last time, the redox reactions are really redox there, put the X. Redox reactions are really one sort of big classification of reactions. They really take care of why a reaction takes place, which is basically an electron transfer. And when that happens, we have things that get oxidized, which basically means that it has lost electrons, and somebody gets reduced or goes through reduction, which means it has gained electrons. And remember, the sort of the consequence of that is you can figure out sort of what is being oxidized, what is being reduced by following what again is referred to as really the oxidation state, kind of like the charge, but not exactly. And we did that little number wheel sort of situation here, number line. And again, if the substance went from the left-hand side of the arrow, reactants to the product side, and it sort of became more positive, that means that it is going through oxidation. If it kind of is moving towards a more negative sort of oxidation state or charge, that guy has gone through reduction. So remember also that they both always happen together. So if something is being oxidized, somebody else is being reduced. So again, the nice thing about that is if you could just figure out one, the other substance is basically going through the opposite thing by default. So that's really sort of the big umbrella of reactions, which we'll talk about more specific ones and look at again, synthesis reactions, decomposition reactions, single replacement reactions. Those are all really under the redox umbrella. The other big sort of umbrella of reactions is double displacement that we also touched upon, and we're going to talk more about today as well. Double displacement reactions can be recognized again by the reaction of two ionic compounds. And always in a double displacement reaction, the ions basically switch partners. So the positive guys always will switch partners. And it will result in two new ionic compounds being formed. And the double displacement sort of umbrella basically accounts for the other two reasons why reactions take place. One of these guys could make a solid, or what is sometimes referred to as a precipitate. And that's another really reason why a reaction takes place. Or some of these guys can make water, which is again really the third reason why a reaction takes place. So ultimately, all reactions are pretty much those three things. One of those three things are happening: electron transfer, solids being formed, or waters being made. And they all sort of fall under these two sort of distinct categories. Really, as we'll talk about here as well today, under the double displacement sort of category, we have things like precipitation reactions when a solid is formed, and we have things like acid-base reactions, which is when water is formed. All right, so again, we're going to go back to the beginning here of the notes and talk about reactions in aqueous solutions. Remember, aqueous solutions are those guys that have the aqueous symbol. It's basically a water environment. And a solution will always have that AQ symbol. And a solution itself is really made up of two parts. There is the smaller part of the solution, which is known as the solute. And there's the larger part of the solution, which is known as the solvent. And that's why when we take something, say like water, which is a pure substance, and we take some sodium chloride and we mix them together, the sodium chloride will dissolve in the water, and it will make a sodium chloride solution. In this particular case, it is the sodium chloride that would be the solute, and it is the water that would be the solvent. Again, typically the name of the solution is always the solute. So whatever the solution is pretty much the solute. Not in 100% of the situations, and we'll talk a little bit about it in later chapters as well, but in a lot of cases, especially with ionic compounds, water oftentimes is a solvent that's used. So that's a very common solvent. Obviously, it's not too toxic. It works really well with ionic compounds to help them dissolve. So one characteristic of what happens when we do reactions sort of in solutions are what are referred to as electrolytes. And electrolytes are substances that when they do dissolve in a solution, they will conduct electricity. And really the reason they're able to sort of conduct electricity is they will produce ions. So because they're able to produce these positive and negative ions in solution, they're able to kind of complete the circuit, if you will, and conduct electricity. There are things that are non-electrolytes, and non-electrolytes can dissolve in a solution like water, or can be dissolved in water, but they actually do not create any ions. And because they lack ions being made, they will not conduct electricity. So they will not conduct electricity because really there are no ions made. Bless you. So there are a couple of different types of electrolytes. A strong electrolyte, as most ionic compounds, or a lot of ionic compounds, are strong electrolytes. And that it means that they will 100% break apart into ions in solution and water. They will not stay together. So if you had a sodium chloride solution, really in like the beaker of sodium chloride solution, that if you put it into a beaker, what you would have is 100% these ions. You would have none of the sodium chloride units still together. All that would be basically floating around are sodium ions and chloride ions in that solution. So none of the units together, completely breaks apart, one-way street to the products. Things like Ki, calcium chloride, also strong electrolytes. As we'll talk about as well, strong acids and strong bases are also strong electrolytes. Because they completely dissociated to ions, they create a lot of ions in that solution, which means they conduct electricity really, really well. So for example, a common experiment is to take a light bulb that has some electrodes hooked up to it. You could put it into that solution, the electrode part, the light bulb would turn on and it'd be very, very bright because it'd be able to conduct electricity really, really well. Now there's also weak electrolytes, and a lot of acids, or some acids, are weak electrolytes. And they actually do stay together in solution. So they stay together in solution. But they do break apart into some ions. So for example, if you had hydrofluoric acid, which is a weak acid, it will break apart into H plus and F minus. The difference between this and sort of a strong electrolyte is in solution, you mainly have this guy. So you mainly have the guys still together in solution, but some of these will be formed. So if you had a solution, again, you would have a lot of the HF units still together, but you would still produce a little bit of the actual individual ions around there. So because it's able to still create a few ions, it's still able to conduct electricity, but it cannot conduct electricity anywhere near a strong electrolyte. So if you kind of do the light bulb example, if you stuck it into that solution, the light bulb would go on, but it'd be very, very dim, almost like it's dying. It's pretty much not a lot of electricity being conducted. So still able to conduct electricity, but nowhere near to that extent of a strong electrolyte. We also can recognize weak electrolytes a lot of times because they will have this reversible arrow, which heads in both directions. It has a forward direction and a reverse direction. So heading towards the product side, sometimes referred to as the forward direction. Heading to the reactant side is the reverse direction. So in this type of reaction, what happens is as you start to make products, at some point, the products will come back together and really break back down and go the other way and make back the reactants. And it will come to what's referred to as chemical equilibrium, also known as Chem 1B. The entire semester is what you talk about that. But basically what will happen is the rate of the forward reaction and the reverse reaction will equal each other. So they'll go back and forth basically at the same rate and basically lock everybody into place. So weak electrolyte will produce a little bit of ions, but we mainly keep it together because that's how it's found in solution. Strong electrolyte completely breaks apart, a bunch of ions, conducts electricity really well. A non-electrolyte, since we have it here, is just something like sugar, for example. If you take some sugar, you dissolved it in some water, it would dissolve, obviously. But sugar is basically carbons, hydrogens, and oxygens, which means it is a molecular compound and is sharing electrons, so it will not produce any ions. And because, again, it doesn't produce any ions, it would not conduct electricity really well at all, basically. Any questions on that there? Now, as I mentioned, water is a really good solvent for a lot of ionic compounds because, as we know from bonding, water is a polar molecule. And that basically means that there's really kind of two sides to water because it's polar. There's a side that's more negative, which is the oxygen side, and there's a side that's more positive, which is the hydrogen side. So water works really well with ionic compounds because, frankly, they're ions when you rip them off from each other. So when they basically break apart, the ions actually get surrounded by water, and that's really what helps things dissolve. So the positive ion is actually going to be attracted to the negative side of water, which is our oxygen side, and basically it'll surround it. The negative ion would also be attracted to water, but it's actually attracted to the positive side of water, which is the hydrogen side. And what that does is essentially allow something that's ionic to dissolve, which is why we visually can't see it anymore, because frankly, it is surrounded by a ton of water molecules, basically, and it's no longer visual to us. We no longer can see it. We know it's still there because I think we did this early on in the semester. If you cooked your sodium chloride water, right, all the water will evaporate off, and then you're left with just a solid, right, your ionic solid back there in the evaporating dish. So the water here works really well because there's a positive side and a negative side. It interacts really well with those ions. It allows those ions actually to be separated from each other and dissolve. And obviously, like I said, if we were to heat this back up, the sodium chloride solution or this ionic solution, we would evaporate off the waters, and that would allow those ions to come back together. And we would once again sort of see that solid appear. So again, very much like those earlier ones where we used the evaporating dish and kind of evaporated off the liquid that was in there, you had some type of solid residue that was left over. Any questions on that there? So this process again is what is sometimes referred to as hydration, as the water molecules basically are able to kind of dissolve all that solid. When you have an ionic solid to begin with, they are arranged in an ionic situation here. And basically what helps things dissolve, right, is we do two things. We usually will stir it, right, if we want to dissolve a solid. When we stir it, we're doing two things. We're adding energy, which helps it all come apart. Secondly, we're also, when we stir it, throwing a bunch of water molecules all over that solid, and that's going to help all those ions kind of pluck off of the solid. So as we kind of mix and stir this ionic solid, that's going to help those ions basically get surrounded by waters and basically start to dissolve. So acid and bases are also electrolytes. An acid is something that can produce H+ ions in solution, so it can produce H+ ions in solution. And a base is something that can produce OH- ions in solution, or hydroxide ions. Also, an acid can produce H3O plus. It is sometimes used. So for an acid, H plus or H3O plus is basically the same thing. So sometimes they're used interchangeable, H plus and H3O plus, which is the hydronium ion. So hydrochloric acid, nitric acid are strong electrolytes. When they are in solution, they 100% break apart into the ions. So if you had a hydrochloric acid solution, H plus and Cl minus, 100% of what you have in that solution are those ions, which means basically you just created a solution that has a lot of H pluses. And that's why it's considered a really strong electrolyte, because it's able to produce a lot of H plus really quickly in solution. There's kind of 6 strong acids: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. These are kind of the 6 big strong acids, which means if you have these guys in solution, they will 100% break apart into the ions. Other acids, pretty much outside those 6, is probably a safe bet that there's going to be a weak acid that you're dealing with. So acetic acid, which is the major component of vinegar, which is this guy right here, is a weak acid. So acetic acid, once again, we do see those arrows heading in both directions, will break apart a little bit into acetate and H plus. Once again, in solution, you mainly have the acetic acid still there. You have just a few of these ions here. So in comparison, if you were to look at a beaker of acetic acid, you would see a lot of acetic acid still together. And you would see a little bit of H plus and acetate kind of breaking apart. So in this case, a lot less H plus is being formed, which is why it's considered a weak acid. It's still able to produce H plus, so that's also why it's considered still an acid in this case, but it would not produce anywhere near the amount of H plus that something like one of these strong acids would do. Any questions on that there? All right, so let's talk about precipitation reactions. And once again, a precipitation or a precipitate is really a solid being formed. And again, that is one of the reasons why a reaction takes place. A precipitation reaction is a more specific classification of what we were talking about earlier, the double displacement reaction. So this basically falls under the double displacement umbrella of our 2 ionic compounds making 2 new ionic compounds. And once again, one of these guys will form a solid, which is our precipitate. So big classification, double displacement. More specific classification of this type of reaction is a precipitation reaction. And let's take a look then. So a precipitation reaction is formed oftentimes by the mixture of 2 solutions together. And because solutions are really basically just ions together, a combination of ions that will come together will make a precipitate, which is an insoluble solid that forms. A precipitate is sometimes abbreviated PPT. So basically what would happen, for example, is you had a solution here that has positive and negative guys. You had another solution that also has positive and negative ions floating around. When you mix those guys together, some combination there will come together and actually make a solid. So one combination of a positive guy and a negative guy coming together will make a solid. You will still actually have some ions still floating around in that solution, but there will be perhaps an attraction to 2 of those. I think we might have done it the other day on Monday. One of those were some precipitation reactions, maybe when you mix a couple of solutions together, you saw some type of a solid maybe form. Not all mixtures will result, obviously, in a solid being formed. So if we take a look at this equation here, we have lead 2 nitrate. I don't know if that 2 made it on your notes or not, so make sure that 2 is there in your equation. Plus some sodium iodide will make some lead 2 iodide and our sodium nitrate. This is a precipitation reaction because you will get this yellow precipitate that is formed. It is also a double displacement reaction. So if we just look at our first guy, this is an ionic compound that's a positive and negative guy together. This is an ionic compound that's a positive and negative guy together. We started this way, we're going that way, I think. Yes. All right, so what happens in this case is we're going to get that double displacement. Basically, the positive guy here will go and hook up with the negative guy on that side. And when it does, it will come together to make this ionic compound here. The other positive guy will then, thank you. The other positive guy will then basically go hook up with this negative guy and make that guy right there. So it's really our positive guys switching partners. Now, it's really important when you do this type of reaction that if you were to write the formulas on this side, you want to make sure that you get the proper formulas first and then balance the equation. You shouldn't try to do both of those things together. So what do I mean by that? This is basically lead with a +2 charge. The basic unit of this is nitrate with a -1 charge. Basic unit of this guy is sodium. And the basic unit of this guy is I-. So just like we talked about with nomenclature, you want to get the right formula. So regardless of what prefixes and stuff you got going on, or coefficients you got going on the other side, that's one lead, that's a +2, that's an I, that's a -1. So again, the proper formula here should be what we have here, which is PbI2. That is 1 sodium with a +1 charge. That's 1 nitrate with a -1 charge. Gives us our proper formula here. Again, you don't want to balance it before you get the proper formulas down. So if you have to predict what goes on the right-hand side of the arrow, take the basic units that make up those ionic compounds, put them together properly like you were doing nomenclature to get the right formula, then go back and do the coefficients to balance. So always get the proper formula, then balance. This obviously is what is referred to as the molecular equation, and this is the balanced molecular equation. But we could also write a couple of different types of equations to really represent what is going on in the actual solution. So if we take a look at this here, we had lead 2 nitrate plus some sodium iodide, I believe. I2 and some NaNO3. And we needed like a 2 there, 2 there, and I think we're good. All right, so this is the molecular equation, but because what we have here are a lot of strong electrolytes, we could write another equation to represent what's really happening when you kind of dump all these guys into the beaker together. What's going to happen is this guy here is going to break apart into ions because it's a strong electrolyte, so it will not stay together. And really what we would have is Pb2+. We would have 2 of the NO3-. This 2 would get distributed to everybody behind it. So we would have 2 of the Na+ because that is a strong electrolyte as well, and 2 of the I-. So both our reactants are strong electrolytes, which means when they're really swimming around in the beaker, they're basically broken apart completely into the ions. On the right-hand side, we do have a solid, and the only way for it to be a solid is it will not break apart. So those ions has to stay together. So when we write this type of equation here, anything that's a solid, anything that's a liquid, anything that's a gas, and anything that is actually a weak electrolyte, we actually keep together. So any of those four things, solid, liquid, gas, or a weak electrolyte, will actually be kept together. So in this case, we have the solid, which we would keep together. And this is just an ionic compound, which means it will break apart. Once again, that 2 gets distributed to both of those. That will give me 2 sodium ions and 2 nitrate ions here. This equation is what is referred to as the total ionic equation. This is sometimes referred to as the total ionic equation. Sometimes people call it the complete ionic equation. This is obviously our molecular equation. First off, any questions on that? So this equation basically tells us what happens when we dump everybody together to mix them. And when we look at the total ionic equation, we should always be able to find on opposite sides of the arrows some ions that look exactly the same. So in this case, the ones that are exactly the same are which ones? On the left-hand side, we have a couple of nitrates. On the right-hand side, we have the same couple of nitrates. Left-hand side, we have a couple of sodiums. Right-hand side, we have a couple of sodiums that are there. These guys that are the same ions on each side, and you also see that you have the same number of those ions on each side. That's because you properly balance this equation. By the way, if you end up with not the same number of those ions on each side, you're not really balanced. So you want to make sure you check it. These are what are referred to as spectator ions. So spectator ions, right? If you are a spectator, you are essentially just watching, right? And that is basically what is happening here with these ions. They are present, are not leading to the formation of the actual solid in this case, or the product in this case that's happening. So what we do typically with spectator ions are we just cross them out on both sides. And again, they should completely cancel out on both sides. It's kind of like subtracting it from both sides. And when we do that, it actually leaves us the third type of equation that we could write, which is an important equation. It leaves us the lead 2 plus the couple of iodides are going to come together and make this yellow solid, in this case, this lead 2 iodide. This reaction is what is referred to as the net ionic equation. And the net ionic equation pretty much cuts down right to the heart of the matter. This is really what's making the product here. This is really what is happening in this reaction. Although there's other ions floating around, when you mix those two solutions together, it is really the lead 2 from the lead 2 nitrate and the iodide from the sodium iodide. They're going to find each other and they're going to make that solid that you see there. Question on those 3 types of equations. Okay, let's take a look at maybe another one here. Why don't you try one here? So let's say we had some silver nitrate, which you might have done the other day, or might do today, plus some potassium chloride. Going to make a little, actually, why don't you predict? Well, no, I'll do it on this side. We'll do it silver chloride plus potassium nitrate. All right. So write the total ionic equation and the net ion. Let's take a look at this one. So once again here, that's going to be a strong electrolyte. So we're going to break it apart. And that would break apart into a silver ion and a nitrate. Also a strong electrolyte, which means it will break apart 100% into a potassium ion and a chloride ion. This being our solid, which is our precipitate here, will stay together. And this also being a strong electrolyte will break apart into K plus and NO3 minus. This would be, again, our total ionic equation. In this case, if we look at it, we could identify our spectator ions as which ones? It is the nitrate, which we see on both sides. It is also the potassium that we see exactly the same on both sides. And they do have to be obviously exactly the same on both sides, and then ions. These again are spectator ions, which we would cancel out. And that will leave us our net ionic equation of what's really happening in this case when you took the silver nitrate and you take some potassium chloride it is that silver ion from the silver nitrate. We'll go find the chloride ion from the potassium chloride, and it will make this white solid of silver chloride, which is our net ionic equation. Question on that there. All right, so you do need to be able to obviously to write the molecular equation, the total ionic equation, and again, the net ionic equation here. Any questions on that? Yeah. You should, when you do this, if you're asking, you should write coefficients and you should write the charges if you're asking. Yeah. Again, they are, especially in the total ionic equation. So ionic means ions. So anything that's an ion should have a charge. And the net ionic equation, same deal. Anything that's an ion should have a charge. The only one that would not have a charge would be the molecular equation up on top. That guy you just write like normal. Yeah. The spectator ions will always be the ions that you can find on both sides of the arrow that look exactly the same in their exact same ionic form. So like NO3 minus on the left, NO3 minus on the right, K plus is on the left, and K plus is on the right. There's a silver ion on the left, but on the right-hand side is connected with the chloride, so it's not exactly the same. So they're not ions that you could cancel out or anything like that. Other questions? Yeah.
For silver, it's like we didn't cross that one out, right?
We didn't, because there was no matching ion on the other side. Yeah. We did, yes. We don't break off the silver chloride here because it's a solid. So the only way it could actually be a solid is those ions has to stay together. Yeah, on the product side, we didn't break it apart because of that. Yeah, so anything that's a solid will always stay together in this type of equations, because basically, like I said, those ions, as they're floating around, they'll come together and make that solid. And, they'll kind of drop to the bottom, if you want to think about it, or start floating around together. They stay together. So they're no longer kind of free ions floating around in the solid phase. So that's why we don't break it apart. Anything that's a weak electrolyte, like we talked about a little bit earlier, you also would not break apart in this type of equation. And anything that's a liquid, like water, for example, would not break apart either. So basically liquids, solids, occasionally you might come across a gas. Liquid, solids, gases, and things that are weak electrolytes, when you're writing these type of equations, they basically stay together. So anything that's technically a strong electrolyte, which is in most cases, most of the ionic compounds that are not solids or anything like that, would be broken apart. Yeah. And then that's how you could find the same ions on opposite sides, obviously, of the arrows. Other questions on that? Yeah. Yeah, pretty much if it's aqueous. Basically what aqueous solutions are pretty much ions floating around. It's basically what most of them are. You could have an aqueous solution that's a weak electrolyte. In that case, you would have mainly the things still together. But most ionic compounds that are aqueous are pretty much strong electrolytes, and they're pretty much just the ions floating around basically in that solution. Yeah. Other questions? Okay. Okay, so that is, I'll just scroll this up here, but that's basically what we just went through on the previous slide there. So our spectator ions. So a good question is, how do I know if I when I combine, for example, two ions together, would I get a solid form or not a solid form? So when we talk about solubility, we could use what is known as solubility rules to help us predict whether or not we would get a solid that would come together as a result of mixing ions together, or two ions together. If something is soluble, it really does mean that it mixes, it dissolves. If something's insoluble, it means that it does not mix. When we look at solubility tables or solubility rules, a lot of times they're broken up into sort of three categories. And more times nowadays, it's really just two categories. There is things that are soluble. So if things are soluble, if you look at the solubility rules, that tells you that when those two ions come together, you would expect a solution to occur. And basically the symbol that those guys should get would be the aqueous symbol. So anything that is basically soluble will get the aqueous symbol. The other kind of big category is when you look at solubility rules, it will tell you that that combination of ions are insoluble, which basically means you will get a solid, and that guy will get the solid symbol. Not used a lot of these days, but still pops up occasionally, is slightly soluble. Slightly soluble kind of leans more towards being insoluble. So if you kind of come across slightly soluble, it kind of leans more towards being the insoluble in a solid. But everything, by the way, even things that are technically insoluble, have some degree of solubility. You can get a little bit of it, a very, very small fraction of anything basically to dissolve, but it's considered overall insoluble because most of it pretty much will not dissolve and will make that solid. So when you look at solubility rules, if it says it's soluble, that guy should get the aqueous symbol. If it says it's insoluble, that guy should get the solid symbol. So let's take a look at some of these rules here. These are rules for ionic compounds in terms of solubility. Anybody in group 1 on the periodic table, if you see an element from group 1 on the periodic table, it is soluble and there are no exceptions, which means as soon as you see a sodium, a potassium, a lithium in a chemical formula, you could just lay up the aqueous symbol next to those guys. You know it's going to be a soluble guy. All ammonium ions, so anything that has NH4 plus in the formula, will be soluble in everything. There's no exceptions to that. Anything that contains nitrate, chlorate, or perchlorate will also be soluble. There are no exceptions. So what that means is pretty much for all these guys here, as soon as you see any of those guys in any formula for an ionic compound, they're all going to be soluble. They all should get the aqueous symbol next to it. Now, when we talk about chlorides, bromides, and iodides, those are usually soluble, but there actually is 3 exceptions. And the 3 exceptions is silver, that's mercury 1, and lead. So if you have any of those guys, they're going to be aqueous if you have chloride, bromide, or iodides. But if you have a chloride, a bromide, or an iodide that has one of those 3 guys with it, then it's going to be the opposite. It is going to be insoluble and we'll get a solid. And that is why earlier, if you remember, we saw our silver hooked up with chloride, right? And that was a solid. That is an exception. Most sulfates are soluble. So most sulfates will get the aqueous symbol, except for calcium and silver sulfate, which is slightly soluble, and barium, mercury 2, and lead sulfate, which are insoluble. So if you have any of these sort of exceptions here with sulfate, then they would become a solid. So that is the sort of exception. Any questions on that there? So these are the rules that you could follow. We also saw a solubility table in our lab, in an earlier lab, where it had like the 2 boxes, you put it together of the ions. Now, there are certain things that are typically insoluble. So these guys typically will get the solid symbol next to them. Any hydroxide will be insoluble. So any hydroxide will get a solid. except if it is group 1, are barium and calcium, which are slightly soluble, then these guys would be aqueous. Really, barium, calcium sometimes are considered insoluble as well. Carbonates, phosphates, and sulfides, again, are typically insoluble, except if it's an alkali metal, which is group 1, or ammonium. Those guys then would get the aqueous symbol. So the insoluble guys, pretty much the only kind of exception is, great, group 1 is involved, which goes back to the other page. Our group, our ammonium is involved. So if I took some sodium sulfide and I reacted it with iron 3 nitrate. Write the products, and also after you write the products, fill in are they soluble or insoluble, aqueous or S next to it. See what you come up with. Take a look. So first off, you should be able to recognize this as a double displacement reaction. That's a positive guy. That's a positive negative guy. So we have 2 ionic compounds. Always in a double displacement, our positive guys are going to switch partners. So that is always the case here. So we do want to put them together properly. So again, you do not want to try to balance and put the equations first. So when we look at sodium sulfide, the basic unit of sodium is a +1 charge. Sulfide is a -2 charge. So that is the basic unit of this guy. Basic unit of this guy, that is iron 3 nitrate, which means the basic unit of iron there is a +3 charge. Basic unit of nitrate is a -1 charge. Now, when we put these together, the sodium that's +1 and the nitrate that is -1, just like with nomenclature, should give me this as my proper formula here. And when I put my iron that's +3, together with my sulfur, that's a -2, common number there is 6, which means the proper formula here should be Fe2S3 in this case. Question on how to put that together properly. I did not care about balancing at this point, right? Now that I have the proper formulas down, I should care about balancing at this point. So to balance it, we're going to lay up perhaps a 3 there. That's going to give us 6 of those, and then we would need 2 of those, yeah? So that would get us our proper balancing in this case. That is the way that you want to do it. Proper formulas, then balance. Don't do them together. Otherwise, you'll end up with the wrong formulas. So especially in this deal, you want just the basic ions, put them together properly so that the charges equal 0, and then go back and balance them. Any questions on that there? Okay. Now that we have our equation here, we want to use our solubility rules to help us decide, what these things are. So when I look at the very first one here, I'm gonna get rid of some of these extra lines, maybe. Get rid of some of those. There we go. All right. So when I look at the first one, the first thing that I see is sodium. And if I look on the previous slide, sodium is group 1, which means it is soluble in everything. That is as far as I need to look. I know this guy is going to be aqueous. When I look at the second one, I see iron, which is not really on my list, but NO3, which is nitrate, is on my solubility table. And on the previous slide, it says that nitrates are soluble pretty much in everything, which means as soon as I see that nitrate, I know this guy should also get the aqueous symbol that is there. Any question on those 2? Looking on the right-hand side, I see sodium, which frankly is as far as I need to go because that is soluble in everything. So I know it's going to be aqueous. If you wanted to, in this case, you could look at the nitrate, which would also tell you it is soluble in everything as well. So you could look at either one in that case. Coming over here, again, may not be able to see iron, but I do see sulfides, which are insoluble except for anything group 1, which is not the case here, right? Or in any ammonium, which is not the case, which means this guy would be a solid in this case. So that is how you could use your solubility rules to figure out what is a solid, what is aqueous. Again, if we looked at some of our earlier one that we looked at, which was silver nitrate plus potassium chloride, gave us some silver chloride plus some potassium nitrate. Once again, going through this, silver may not be on the list, but nitrate is soluble in everything. So that is how I knew this was aqueous. Potassium is group 1, which means I know it's going to be soluble in everything. This is chloride, which is soluble in everything except for silver, lead, and mercury. And that would make the exception here. So chloride is usually soluble, but when silver is involved, lead 2 or mercury 1, it becomes the opposite. And that is how I knew earlier that that was a solid. And once again, I see potassium, which tells me it's soluble in everything. And that is how I, again, know earlier that the silver chloride was the solid. Question on solubility rules or how to use them. All right. So acid and bases are really the type of reactions that lead to the formation of water, which again is the other real reason why reactions take place. Acids have sour taste. They cause litmus paper to change color, like we used litmus paper the other day. They actually will cause litmus paper to turn red, as we talked about. So if your litmus paper turns red, it's acidic. They react with metals to produce hydrogen gas. You've done a number of those, including the other day when you put the magnesium, the hydrochloric acid together. The bubbles that you saw when you held your finger over it was the production of hydrogen gas. And acids can conduct electricity because they're strong acids, which conduct electricity really well because they're strong electrolytes, and weak acids, which are weak electrolytes and will still conduct electricity. Bases have a bitter taste. They feel slippery. Most bases are soaps and stuff like that. Drain cleaners, a lot of the bases. They changed litmus paper to blue. So that experiment that I did with the calcium, we produced calcium hydroxide, which is a base. And that is why the litmus paper turned blue the other day when we did it together. And again, there's strong bases and also weak bases, which will conduct electricity because strong bases, again, are strong electrolytes and weak bases still are weak electrolytes that can conduct electricity. Once again, acids will basically produce H plus or H3O plus in solution, and bases will produce hydroxide in solution. So that again is your really basic definition of each of those things. When we look at acids, as I mentioned earlier, again, a strong acid is a strong electrolyte, 100% going to break apart in solution. And as we talked about before, there are those 6 sort of strong acids you should be familiar with as you go through your chemistry career, because they do come up a lot. And again, those 6 that I listed earlier are all strong acids. They're all strong electrolytes, and they all will 100% break apart in solution. So when you have something like nitric acid in solution, it's all the ions. None of the whole unit is still together. Bases, as I mentioned as well, on the other hand, are, I'm not sure why that's an equals, but this should be a plus. Bases, on the other hand, again, are the guys that produce hydroxide. If you look at the periodic table, right around, lithium or sodium, kind of coming down to calcium, hang a right, come on down. Any of those guys that have hydroxide in the formula, like sodium hydroxide, potassium hydroxide, calcium hydroxide, those are all strong bases. So a lot of strong bases come from group 1 on the periodic table and group 2 on the periodic table. Group 1, if you remember, are the alkali metals. Group 2 is the alkaline earth metals, and the word alkaline means basic. Yeah. So a lot of strong bases come from group 1 and group 2 on the periodic table, and they have hydroxide actually in the formula. So if you have something like sodium hydroxide in solution, once again, it would 100% break apart because it is a strong base. And that's why it's really a strong base, because it will 100% break apart in solution and produce a lot of hydroxide ions really quickly and make the solution basic, really, because it's able to do that. So when we react a strong acid and a strong base together, what basically happens is the formation of water. And that's why it's sometimes referred to as an acid-base neutralization reaction. The fundamental change of any reaction of a strong acid and strong base together, this is the net ionic equation you get, is basically the formation of water. It is the H plus from the acid getting together with the OH minus from the base to make water. And H plus and OH minus have a really high affinity for one another. So if you take something like hydrochloric acid plus some potassium hydroxide, that is a strong acid, strong base. By the way, it is also still a double displacement reaction. That's a positive guy. That's a negative guy. The H plus and the OH minus will come together to make water. The K plus and the Cl minus will come together to make, if I could write it right, there you go, KCl. This makes always in this reaction water and what is sometimes referred to as a salt. So water and a salt is made as a result of this reaction. If we went through our total ionic equation in this case, HCl, which is a strong electrolyte, would 100% break apart into H plus and Cl minus. KOH, which is a strong base, will 100% break apart into K plus and OH minus. Water, which is a liquid, much like a solid, will stay together. It is sharing electrons, not going to break apart into ions, it's molecular. And potassium chloride, which is a strong electrolyte, will break apart into K plus and Cl minus. That would be our total ionic equation in this case. We could see here that our spectator ions in this case are Cl minus on both sides and our potassium on both sides. Those are going to be our spectator ions, which we could cancel out. And that is going to leave us, again, the net ionic equation that's happening here. Once again, it is the H plus from the acid coming together with the OH minus from the base to form H2O, which is water. And again, one of the reasons why this reaction is taking place. Any questions on that there? So that pretty much is your net ionic equation you will always get in any combination of any strong acid and strong base come together. That's pretty much the formation of water. And again, as I mentioned, that's why they're sometimes referred to as neutralization reactions. So these acid-base neutralization reactions fall really under the big umbrella of double displacement reactions. The end result is the formation of water. Just like we talked about the precipitation reactions, which also fall under the double displacement umbrella, the end result of that reaction is a solid being formed. So again, those are the two of the three reasons why reactions take place. So again, this is very similar to the one we just did there. That is hydrochloric acid and sodium hydroxide. And again, you can see our spectator ions being these guys, leaving us with the same net ionic equation, basically water being formed. Now, as I mentioned before, another thing that's formed as a result is what is referred to as salts. And salts is, I guess, a fancy word for really just an ionic compound. So oftentimes people will say when you react an acid and base together, you get a salt and water that is formed. So an acid and a base gives you salt and a water. And I say most cases based on solubility rules, your salt's going to probably be soluble. It's going to be aqueous. There is a weird couple of places where it might not be, but probably 9 times out of 10, your salt part's going to be the aqueous and your water obviously is left over. Question on double displacement reactions, net ionic equations, total ionic equations, molecular equations. All right, so let's then get back to the other big classification of reactions, which we delved into last time, which is really redox reactions. And again, that oil rig, or Leo the lion goes grr. As we talked about earlier, something goes through oxidation. It has lost electrons, becomes more positive. Something goes through reduction. It has gained electrons and becomes more negative. And again, you can use that number line to help you out. Becoming more positive, once again, will be oxidation, and becoming more negative, reduction. Outside of acid-base reactions, precipitation reactions, which are all under the double displacement umbrella, pretty much everybody else is going to fall under this umbrella. And again, redox reactions takes care of those electrons being transferred. So let's take a look at some of this here. I think we did this last time. Oops. But again, if we look at sodium, which is by itself, it really has no oxidation state or charge, and that goes for any element in its natural state that is uncombined. The chlorine, that is naturally how chlorine comes as a diatomic molecule. Remember that they only kind of gain charges when they come together. So the sodium here would be +1, and again, the Cl here would be -1 in this case. So if we looked at our sodium, it is starting at 0 and ending at +1, which means it is becoming more positive. And that means here the sodium is going through oxidation. The chlorine is starting at 0 and ending at -1, which means it's becoming more negative, and it is going through reduction in this case. And by the way, that is always what happens when you have a metal and non-metal together. And always when a metal and non-metal come together, my electron is way off, of course. It is always the metal that is going to transfer the electron to the non-metal. So as we talked about with ionic compounds, it's always a metal that becomes positively charged. It means it lost electrons, and it's always a non-metal that gains it, which becomes negatively charged. So figuring out oxidation and reduction for an ionic compound is really simple. The metal should always be the one being oxidized. The non-metal should always be the one that is being reduced. Any questions on that there? Okay. So that is a oxidation reduction reaction. This is one that we did the other day with the ribbon. That's magnesium and oxygen come together to make magnesium oxide. If we look at the magnesium here, 0 in terms of its starting oxidation state. Oxygen, that is naturally how it comes. But when the magnesium comes together with the oxygen, that is when the magnesium has a +2 charge. The oxygen has a -2 charge. And if we just look at our overall charges here, the magnesium started at 0, ended at +2, which meant it is becoming more positive. So it is going through oxidation, which is what we would expect. By the way, once I figure that out, I know oxygen is going through reduction by default. So it does the opposite thing, but we could also look at it. Oxygen starts at 0, ends at -2, becoming more negative. So the oxygen here is going through reduction. So this is also a redox reaction that's taking place. Electrons are being transferred from the magnesium to the oxygen. We could represent that by these two equations. The magnesium is losing electrons, which the electrons end up on the product side. The oxygen is gaining electrons. Electrons end up on the reactant side of the arrow. Those are sometimes referred to as half reactions because it explains half of what's going on, what's being oxidized and what's being reduced. And again, that is the half reactions that are taking place. And in a half reaction, anything that's being oxidized, electrons on the product side. Anybody being reduced on the reactant side. All right, so again, redox reactions is that big umbrella of which more specific classifications can be used to classify reactions. So I think we'll talk about some of those. We're not going to worry about involving nonmetals right now. So let's talk a little bit about classifying reactions. The three reasons why reactions take place, as we've been talking about: a precipitate form, some type of solid, water is being formed, or again, a transfer of electrons. As we saw earlier, a more specific classification of double displacement reactions is a precipitation reaction as a solid is being formed. So again, this is an example of a precipitation reaction, which is still a double displacement reaction: positive, negative, positive, negative, positive guys switch partners. So double displacement, more specifically classified as a precipitation reaction because, again, a solid was formed. In this reaction, that is referred to again as a double displacement reaction, and always can be recognized by the presence of two ionic compounds. So if you see two ionic compounds, you should just go into automatic mode and switch the partners around, and that is how you will get to the products on the other side. And again, that is what we see up here as well. That is our acid-base reaction, which is again sometimes referred to as acid-base neutralization reaction, as we talked about a second ago. Again, also falling under the double displacement umbrella, as that is a positive negative guy, positive negative guy. Once again, positive negative guys switching partners, formation of water in this case, which is ultimately what is happening. All right, so this is a redox reaction that's happening. In this case, we can look at our lithium, which is 0, our fluorine, which is 0, on this side, +1 and -1. Once again, lithium is starting at 0, ending at +1, becoming more positive, being oxidized. Fluorine starting at 0, ending at -1, becoming more negative, being reduced. A more specific classification of a reaction that falls under redox is a single replacement reaction. And in a single replacement reaction, you pretty much have either a metal or a non-metal that is not attached to anybody else, just by itself, and you have an ionic compound like this. So what happens in this case, for example, is the zinc that is no charge becomes +1 here and -1 here. Zinc, when it does have a charge, is normally positive, so it will kick out the positive guy in this case. And the result of that is when hydrogen comes out by itself, it comes out as hydrogen gas, like those bubbles you saw when you did it with magnesium the other day. The result of that is zinc will now gain its normal charge of +2, and chloride is still -1. So those two guys will then come together to make zinc chloride, which is aqueous. And also we would need to do a little bit of balancing there. So I think we are balanced at a point. So we end up with something like this. So this is a single replacement reaction. Somebody comes in and kicks out somebody else. Yeah. It does, because when hydrogen is by itself, it actually will gain back the electron that it sort of lost, right? So that's why it was H+ to begin with, right? It was short an electron, so it gains back that electron now, right? And becomes basically just regular hydrogen, and the normal form of hydrogen is H2, a gas. Yeah. Other questions? In order for this reaction to actually take place, is whatever coming in needs to be more reactive than what is replacing. So if we saw this happening here, the zinc would be more reactive, obviously, than hydrogen. If you did the same reaction but used copper, it would not take place. Copper is actually less reactive than hydrogen, so this reaction would not take place. You could also do this type of reaction like we did with the halogens way back when we did that experiment with the different layers. That was also a single replacement reaction. So if you had something like chlorine plus some sodium iodide, this chlorine would come in and kick out the negative I there. The I2 would come out by itself and make some sodium chloride at that point. Do a little balancing there. So you could also do this with nonmetals. If it's a nonmetal you're starting with, it will replace the nonmetal. If you're starting with a positive metal or a guy that normally is positively charged, it will replace the positive guy. Question on single replacement. Different than double displacement, because double displacement again has two ionic compounds that you're starting with. All right, let's talk a little bit about the combustion reaction. I don't think we got too much more to go, so I think we'll just kind of wrap up hopefully here the last little bit. So in a combustion reaction, most of the time we're talking about the truly organic combustion reaction, and that is the one like we did the other day when I put the Bunsen burner on the bench. That was this guy right here. That is methane reacting with oxygen in the air. You get fire. We were able to actually see the water being formed when we hit it on the cold bench, right? We saw the condensation occur. But in a traditional organic combustion reaction, you start with an organic guy, which has carbons, hydrogens, maybe oxygen. There's always O2, and you always make CO2 plus water. So that is your classic organic combustion reaction that takes place. Now, a more generic combustion reaction is the definition of, frankly, you just need oxygen involved. So if you actually just see oxygen on the left-hand side of the arrow, it technically could be classified as a combustion reaction. But I would say probably 9 times out of 10, most people are thinking of the organic combustion reaction, like we were just talking about there, where you always have O2 and CO2 and water being formed. Question on that one there. Usually heat and energy, like our Bunsen burner. Think about propane, right? Butane, right? Those things you light, right? They catch on fire. A lot of those things are combustion reactions that are occurring. Last couple of classifications of reactions is a synthesis or combination reaction. Synthesis or combination reaction, basically you take two things and put them together, hence the name combination. So hydrogen gas, oxygen gas makes water, two things make one. Sodium chlorine makes sodium chloride. Magnesium plus oxygen, like we did there, to make a little magnesium oxide. Two things make one thing, right? That is a synthesis or combination reaction. This is also a redox reaction that's still happening with all these. These are all oxidation reduction reactions. And by the way, this also has O2, which means you could classify it as a combustion reaction. So this one reaction here could be classified as a redox reaction because we have an electron transfer happening. Could be classified as a synthesis or combination reaction because two things make one thing, or it could be classified as a combustion reaction because there is oxygen there. So as you can see, you could classify the same reaction in a few different ways depending on what you're looking at. There's usually a better choice that most people would probably call this a synthesis reaction or combination reaction, but you could classify them obviously as the other two. So synthesis, combination, putting it together. The last type of classification is a decomposition reaction, which is basically breaking it apart. So it's really the opposite of a synthesis or combination. It's basically one thing that you break apart into maybe two or more things. So like you did the other day, the electrolysis of water. One thing broken apart into hydrogen gas and oxygen gas as those guys started to bubble through. This is still, by the way, just looking at it here, this is still a redox reaction as well. Hydrogen is like +1, oxygen is -2, and these guys are 0 in this case, yeah? So in this particular case, in this reaction, the hydrogen is starting at +1, ending at 0, which means it's actually becoming more negative. So in this case, it is actually the hydrogen in water that is being reduced. The oxygen in water started at -2 and ends at 0, which means the oxygen here is being oxidized. So this is also a redox umbrella, and it is classified as a decomposition reaction. If you have some carbonic acid, we kind of saw that in an earlier one, it will decompose into water and CO2 gas. Kind of when we did the Alka-Seltzer tablet, the other experiment. Decomposition reaction there. So to summarize the different types of reactions and sort of where they fall, if we look at our double displacement reactions, which is again the big umbrella, underneath there more specifically, you could have a precipitation reaction. You could have an acid-base reaction. Under redox reactions, where we have electrons being transferred, that's our synthesis, combination, our decomposition, our single replacement, and our combustion reactions. So those are sort of the big umbrellas of classifications and the more specific classifications that fall underneath there. Any questions on classifying reactions? All right, that wraps up chapter 7.